Thanks a lot for a very kind introduction, and yeah, very happy to be here to share our recent work and also our thoughts about the learning robotics. Particularly, I will talk about our efforts how to make more reliable and more trustworthy. So first, I want to thank all my colleagues, especially these are my students who contribute a lot to all the slides I will show today. So in recent deep learning in robotics have achieved great performance. Drone racing to like locomotion in super harsh environment, and to the super diverse manipulation. And Boston Dynamics recently also a lot of super nice skill with learning. So for my side, actually, I start to work with Professor Michael Hutter on reinforcement learning from 2020, and we also saw a lot of very successful use case of deep learning, and it's really very robust performance both indoor and outdoor. And this year, ICRA, we have a paper even collaborate industrial collaborator, which is Sony, and we deploy the reinforcement learning on the Sony eyeball robot to make robot work more correctly in-house. So just a very brief background for just in case some people not familiar with deep reinforcement learning. So deep reinforcement learning, the deep means like we are trying to use a deep neural network. Reinforcement learning, like we want to do a lot of trials and errors, either maybe in a simulation because it's super efficient. Then here is one very important question. So far we see so many successful cases in robotics with deep reinforcement learning, even recently DeepSeek, right? Also it showed some results. Does reinforcement learning already solve all the robotic problems? So what's the currently main bottleneck of deep reinforcement learning? So first, still need tons of samples. I will very soon explain why it will be a problem in some cases. And second, there's still a lot of simple mismatch. And last but not least is the black box neural network system. So what's something maybe not happy about some challenge were caused by this limitation. Until today, I think we now see many successful cases for perspective influence learning directly with deep reinforcement learning. And second, because the simple mismatch is still huge for especially context-rich tasks. So we still need a lot of very high fidelity simulation software to help us. And last, because reinforcement learning and also other learning-based methods, our system still black box neural network system. For example, for some very safety critical tasks like this SpaceX task, I think that's still not, we don't have a courage to take the risk to use it. So in my lab, our research goal is not only want to make a more intelligent system, but also make more safe system. The important trick for us is simulation. So today I will mainly talk about these three topics. So first, I want to talk about how we can handle high-dimensional end-to-end reinforcement learning problem, maybe with different simulation. So first, I want to show like we just say this very successful drone racing example from Professor David Samusa, right? If we look very closely at this example, actually it's very low for your task. Mainly, for example, the drone racing just 31 dimension in one of their nature paper. But however, for it's really perceptive end-to-end navigation or we say local navigation task, the input is more than 1,000 dimensions because of image or depth image, super high dimension. So then it makes very difficult. Why? The reason is like the traditional reinforcement learning, we only do forward. So for people who train reinforcement learning, you have to do a lot of random sample and to try to get a grading based on the samples. So that's why it's very sample inefficient. And imagine you have 1,000 input 6-dimension system, that's so difficult to kind of draw out to get the result. And recently we have some very nice different simulation. The different simulation means like for data point, you can directly calculate the reading information to get you from the observation to go back to your from your result for observation, you have to help you to update your control policy. So one example we will show in ICRA is like So this example is we work on the leg robot, and our input is a depth image, and directly from end-to-end reinforcement learning, we can train this robot not only work, but also avoid the obstacle. And Andrew, who is my master student, work with us, and he will demonstrate his result on Wednesday in ICRA'. So one important trick is like, because it's still very difficult to get stuck into some local minima. So one important trick we have is like we add something we call Pinocchio tricks. So we can somehow like look ahead for some distance to help the robot some obstacle to get within in advance. So that one we just achieved in a simulation, and recently we try to push this similar method on a drone. For example, this is a drone case, and the right is the depth images. Try to observe during the maneuvering. And we are working hard towards to achieve this in real, to deploy this system in a real robot. Okay, so that's the first part. So we feel like the high-dimensional end-to-end learning is still a big challenge, and we are strong believer like the new advanced simulation, like especially differential simulation, can play an important role here. And second is like, so I mean, this is also my previous colleague called Mei Yang, and they developed super nice. Longtime they called Orbit, recently called JSK Lab, and to show like this kind of even deformable object manipulation, right? I mean, in simulation it looks super nice, but if we ask ourselves, actually we still cannot see this kind of thing in real hardware. So why? I think one of the main reasons is because simple real is still very challenging and not solved. So contact, for example, previously we showed the leg robot, but contact is still relatively simple. For example, for this robot dog case, it's less than 100 triangles to calculate its contact. But for manipulation tests, a lot of tests, for example, like this example, is more than 10,000 what is the triangles and so on. So try, in order to not only to make it very accurate, but also very fast, it's still a big research challenge. So thanks to my very talented student, and we work very hard to build some innovation from low level. So this one is like we're trying to renew some contact solver method, and to not only to make this contact-rich test not only fast but also accurate. And we have some benchmark tests to show our method within a real-time budget. Relative error is quite relatively small compared to the ground truth data. We can limit it to 0.1%. And you may ask, what's the trick? Is just we, unfortunately, it's like a student develop a lot of new mathematical methods, and also student code by CUDA language in order to speed up some hard code improvement or credit up to the students. So some comparison to show why the simulation is important, like for example, for this case. So this case is to show, so this slope is 10 degrees. And for the mu, if the simulation is super accurate, it should be around 0.176 or something when this cube will start to sleep. And we compare different methods. Like for our case, we can be super accurate to kind of 0.001 to show the difference. For this simulation, you have to be kind of different, be larger than 0.1 to show like one is sleep, one is not sleep. So if we compare some detailed simulation we use every day, so first we compare bullet, we found bullet, the sensitive kind of nearly 0.01. And the Mojuko somehow, even we use a PGI solver, somehow it's less sensitive to this kind of change. And we make some more detailed comparison to show like even for this very basic rigid body contact, still a lot of simulation nowadays, we need to improve the solver to achieve very high accuracy contact. So just imagine if we have a very nice simulation, not only support rigid body, but also deformable object. we can unlock a lot of new possibilities, especially in safety critical application. For example, some cases are shown in SOFA. SOFA is one of the very famous medical simulation. And my student integrate their contact solver to this simulation to achieve very state-of-art result in this deformable object. One case is a haptic headband. Another one, from going, imagine you insert a needle and we can manipulate some tissue and so on. So this one not only we can use for the policy training, but also can be used for doctor training and so on. So also some benchmark we show is like, okay, our method compared to the complete Newton method will almost achieve a similar performance. Newton method is great, but just, it's very time consuming. So we are trying to emphasize we are under the real-time budget to achieve such kind of result. Yeah, nowadays we try to push forward for our simulation to even for some articulate object. So maybe next year I can show more on this part. And then you may ask, why, as a robotic lab, why you put so much effort on simulation? So one first point is like it's very helpful for us to do policy learning. Another thing I really want to emphasize is also super useful for policy validation or for robustness assessment. So why we want to do robustness assessment? So first, some storytelling is like, so previously, based on my experience, we found actually reinforcement learning is super good in real world application. But however, every time there is, some industrial visitor that came to our lab, or they will always ask, okay, neural network controller is great, but I need some guarantee. They'll give me some guarantee. So unfortunately, like today, I think Professor Luca worked a lot on this part. So for me, I'm sorry, I cannot give you a guarantee. But what I can give is I can help you to do some assessment. So yeah. So some background is, the background from this work we published last year RSS. The background is like recently the lag locomotion achieved super great result with deep reinforcement learning. It's not previously not only in in some research, but also recently you see Unitary and so on, many industrial they also use this controller. But then there is one important issue is like if we ask the people when your controller will fail, I asked my colleague Takanishi when will your controller fail. Also, the people who design it is not super confident about your worst case. I think that's a problem. And second is like it's very easy to train multiple policies. Like we change a little bit neural architecture, we change a little bit of reward. But what is better? Which policy is better? Still, such kind of comparison is very difficult nowadays. And what's worse is like nowadays the controller become better and better. Finding a failure case will become long tail. And meanwhile, control problem is a time sequential problem, means the searching dimension is super high. So first we compare with some standard testing. For example, we add some constant force, we add maybe some random force, we found it's very difficult to fail even open source controller. And also very interesting thing is like we hold a kind of the AI safety challenge inside the lab. So we invite almost 100 people who are kind of expert in act like robot and to ask them to go over this robot. But unfortunately, 3 people can do it, and even though it's just an open source controller, which means very simple. But if we compare to some computational method, if this is computational method, the result is very interesting. So the winner, compared to the winner, the computational adversary method, the survival time is much shorter. It's like only 1.3 seconds. It will find the strategy will make the robot fall over. Meanwhile, the falling angular velocity is much higher, means the damage is higher. So I think this example really to show is very important that we need a computational method. The domain expert knowledge is very difficult to, such kind of intuition is very difficult to find the failure case for modern system. And after that, we try our state-of-art control policy. So previous one is just the open source language, very simple policy, MLP policy. And then we test on the macro world-based controller, which win the data robotic challenge. And we are also very surprised to find like we just apply very small adversary signal. Here is like we assume the robot state time estimation has no more than 3-degree error, which is very small. The state estimation location go no more than 3 degree. And meanwhile, we assume like the user can play around the joystick, but also we constrain only to 0.5 meter per second. This robot during the operation range is almost 2 meters per second. So very mild signal, we can make the robot fail. Then people may ask, do you just randomly play around the joystick to feel it? So we found super interestingly, like every time for the stair terrain, the learned adversary will always first rotate the robot to be parallel to the stair and then start to attack. Because when you're parallel to the stair, it's very easy to cross your legs to make the robot forward. But in flat terrain, we never see this kind of thing happen. So we found it's really adversary learn some real failure case. So here we just want to show we also have some technique to make the adversary as realistic as possible. So after we find the failure case, one more thing we can do is to improve the robustness by trying to gather this with these failure examples. So left side is original controller, and right side is our robust flight controller after this robustness assessment. So by finding the real corner case weakness of our controller, we can further train together with this very challenging corner case to make previous robot controller more robust. So this is just to show you some very super harsh environment for like robots. So yeah, so after that, my colleague who designed the previous controller said, "Oh, I don't trust. I want to test by myself." I said, "Yeah, please." So this guy is the guy who developed the original controller. He tried to do very hard stress test on this robot to show whether those can really help to make controller more robust. And we also show some outdoor experiment. I just skip here. So our method is not only just target for some reinforcement learning based controller, but we can very easily find the failure case in other controller. So this controller is the MIT Mini Cheetahs controller, which is also golden standard for like robot MPC controller. We find it super easy to find the failure case with this MPC controller. And also we have some technique how to encourage the diversity in the failure discovery, but we just don't want to just find one failure case, we want to cover as much as possible. So some takeaway of this work is like first, we think attacks can be used as a robustness indicator to compare a little bit other different robustness, different controller. Second, very interesting, we found that multi-modality attacks are usually stronger. So our attack space can be from a command space, observation space means the state estimation error, and the P is perturbation space, like perturbation force. We found only one single space modality can never make this very robust controller fail. But if we can combine the two space together, the result attack result can be much stronger. And third, we found actually the current domain randomization is not sufficient to make the controller robust enough. So one example is like during training, maybe we apply random 100 Newton force, very common nowadays. But we found the adversary can very easily build a robot within this range, which just means the domain randomization cannot guarantee you are robust enough. And last, it's like we found the adversary can be very smart. It's really learn something. It can leverage the terrain to find the failure case. And the human intelligence is not enough. We really need a computational method to work together with us. So yeah, I'm happy to show some more recent case. So imagine for this robot, this we call ARMA, which is a robot with a manipulation arm. So anyway, you can guess what's the weakness of this robot. Imagine you can add some random perturbation force on the effector. What's maybe the failure case? I can show what's learned by reinforcement learning, what's AI learned failure case. One failure case is very smart to try to push the robot towards the end effector to hit the ground. And eventually it will make the robot also forward because the central mass is lose a balance. And second is kind of failure case is learned by itself is to make the robot to hit itself by this way. Yeah. So it's all self-discovered by the learning-based method. And after trained together with this failure case, we can make the controller more robust. Every time when we want to do some adversary behavior, it's trying to actively react to this case. So the proposed method not only just works for the leg robot, but recently we also pushed to manipulation. This one we work with some NVIDIA people to test their NVIDIA doctrine manipulation policy. And also for navigation and so on. So far we show like, okay, so we want to have a very nice simulation in order to not only for policy learning, but also we can do policy validation. For policy validation, there are still some problems for assessment. So first, I will be very honest to say still we lack diversity. So usually our method will converge to one specific case. It's very difficult to guarantee to cover all the bigger case. Second, still computational expensive, especially imagine you are searching for a long tail, meanwhile it's time sequential attack sequence, very difficult. So again, one thing like we can reuse our framework simulation because it can avoid a lot of samples and directly use the breathing to guide you for the searching. So some inertial trial is like, okay, we can already to show in some this work, different simulation, we can find a failure case of the robot controller. And the second also last point I want to mention is like, so far we show, okay, we can find the failure case, we can do the assessment. But if you think it deeper, it's actually still the blank box, blank box, right? You feel like maybe something weird, we want to make it more transparent, but still like blank box, blank box. Is there any possible to make it more white box? So here I want to briefly introduce one of our very inertial attempt to use a white box transformer. So white box transformer is not developed by us, but developed by some researcher from Berkeley who try to show the the information can be explicitly compressed with some specific design and rate reduction and so on. So I think maybe we are one of the first team to demonstrate to show it on the locomotion. So here we should. Sorry, first video is broken. But anyway, I just want to show after many trials and errors, we found the black box transformer won't sacrifice the performance too much. Meanwhile, it has some advantage because it can explicitly to tell you how the information is reduced. So we can use this to, one case is we can use this to compare like how many layers we really need in our neural network design. We found actually near the 7 or 8 layer, the information already reduced to almost to the lowest level. So which means maybe we don't need more layers for the robot control. Yeah, but still for this point, I think still a lot of things can be explored to make the whole system more transparent. All right, so I think now going to my final slide for the conclusion of today's my introduce. So first I introduce the current reinforcement learning, what that look like, what it can work and what maybe cannot work very well. So for conclusion, it's like for very high-dimensional perception-based decision-making system problem, still the current response learning do not work super well. And we believe that for different simulation can play a very important role there to make us to help to solve this high-dimensional decision-making problem. And second, I've said that simply we are still not ready and not found to prevent a lot of contact-rich robotic tests, which like manipulation, especially for manipulation. And last, for the safety critical application, still does not work. Maybe because we don't have any guarantee for the safety critical applications. So our research goal is to build a more intelligent and safe system. So for intelligence, we like to leverage different simulation, programming, and so on. And meanwhile, we hope to improve the safety, not only to do the robot policy learning, but also do the policy assessment. Our key weapon or our something key here is to the next generation simulation. Where video simulation will be very important as a data flywheel for us, not just the imitation learning from the real world, but still we need the simulation to not only for policy learning, but for the robot-based assessment. Yeah, so far I think I can conclude my presentation. So first I want to thank for my previous supervisor and also a lot of collaborators in ETH previously. And also some of my current students. So our lab just started last year, June, I think. So today maybe almost 1 year. And we are still new lab, and we are very excited to be in this community and looking forward to more communications with you all. Thank you very much.